Okay, so today guys what we're going to have a look at in video 3 is a new concept to you, which is the empirical formula, and later on in the video we're going to convert empirical formula into molecular formula. So firstly we need to know what exactly is EF, or empirical formula. Well, it is the simplest whole number ratio of moles of atoms or elements in a compound, CMP short for compound. So in other words, we need to be able to calculate out the number of moles of an element within a compound, and so we will go back to our old formula, the equation that we used earlier, where N for number of moles is equal to mass over the MR, the RFM, or the RMM. So if we take a very simple example, if we had two substances A and B, and we discovered that there was 0.5 moles of A in a substance, 0.25 moles of B in a substance, the simplest whole number ratio of those two values is 2 to 1. That would give us an empirical formula of A to B, 2 moles of A per 1 mole of B, essentially. So let's have a look at a worked example on the next page. Okay, so this looks a bit messy at the minute. We will probably just tidy that up and we'll start again. So in this instance we have been given the percentage of an element in a compound. So this particular compound is a hydrocarbon, and we have got 75% note carbon and 25% of it is hydrogen. Well, you might say, well, you haven't taught us how to convert percentage into number of moles. Well, you're right, I haven't. But if we make the assumption that we have 100 grams of this hydrocarbon, therefore we can assume that 75 grams of that 100 grams is carbon and 25 grams therefore must be hydrogen. So we can just simply convert the percentage straight into mass, and that's exactly what we do. Now, using our formula from the last video, where number of moles equals mass over mass of 1 mole, MR, we can very simply convert these into moles. The molar mass, or the atomic mass, or whatever you want, of the carbon is 12 and of the hydrogen is 1. So therefore the number of moles, the number of moles is mass divided by the atomic mass, or in other words 6.25, 25 over 1, which is obviously 25. We then take the smallest value from the previous calculation and divide it into the number of moles for each of these. Smallest value obviously being the 6.25, and 6.25 divided by 6.25 is obviously 1, and 25 over 6.25 works out at 4. That means we have 1 mole of carbon to 4 moles of our hydrogen. So we can represent it like that, which wouldn't be ideal. We just take the little 1 out, and the formula is indeed CH4, or in other words methane. So I'll do a worked example on the next page, and then I will hand it over to you to do a few. So this is a hydrocarbon again, so it contains carbon and hydrogen only, and in this instance we have 80% carbon, 20% hydrogen. So again, we very simply take the percentage of carbon and turn it into mass, and percentage of hydrogen and turn it into mass. We then take number of moles by taking that mass and dividing it by the RAM, and we do the same over here. So this works out then at about 6.67, and this obviously works out at 20. Okay, so if we work from there then, and we take the smallest number, which in this instance is 6.67 and 6.67, we should be able to work out from that that the simplest whole number ratio here is 1 to 3. So our formula is CH3 and not C1H3. Remember, we don't put the ones in. Okay, so if we move on then to number 2, which is made up this time of nitrogen and hydrogen. If you pause this video now, I will put the answer up. So pause now, please. Okay, the answer to that is 1 nitrogen, 2, 3 hydrogens. Okay, if we move on to the next one, where we have a compound made up of 51% calcium, and the rest of it must obviously be 100 minus 51, which is therefore 49% of that compound must be fluorine. Okay, so if you pause the video now, I will put the answer up. Okay, so the answer to that is calcium 1, fluorine 2, so it's CaF2. You should have had 51 over 40, and you should have had 49 over 19, and that would have given you then your ratio of 1 to 2 calcium to fluorine. Okay, let's have a go at another one. So this one is slightly different in that it contains 3 different substances. So if you pause the video now, I will put the answer up. So we have sodium, we have oxygen, and we have hydrogen. We have sodium sitting at 57.5%, we have oxygen at 40%, and we have 2.5% of that. That should be divided by 23, that should be divided by 16, that should be divided by 1. That will give us, if we continue through the calculation, a ratio of 1 sodium to 1 oxygen to 1 hydrogen. Okay, and that means that our formula is NaOH. It's actually sodium hydroxide. You have 1 sodium to 1 oxygen to 1 hydrogen. Okay, let's go and have a look at another one. This time we have a compound called nitron, which is an ammonium fertilizer, and it is made up of nitrogen, hydrogen and oxygen. So again, have a look at it, pause the video now, and I will put the answer up. So nitrogen, hydrogen, oxygen, we should have had 60 over 16, 5 over 1, and 35 over 14. That should have given you a ratio then of 2 to 4 to 3, and therefore an empirical formula of N2H4O3. Okay, so for another worked example, this time it should actually be simpler, because instead of working in percentage, we're straight into mass. So the method for this is exactly the same. We have been given a mass of magnesium, a mass of chlorine. The molecular mass of the two things we then go and find out from the periodic table, and we work out moles by doing mass divided by the atomic mass in both instances, and we get a ratio in this instance of 0.08 to 0.16. We take the smallest number, which is obviously the 0.08, and we divide it into both the other numbers, and we get a ratio of 1 to 2 in that instance, and that gives us Mg1Cl2, or the way we write it for an examination answer, MgCl2. So we'll do the same thing again. I will put a few up on the board and you can work through them. So if you pause the video now, I will do the answer for you. So 2.7 divided by 27, that is for our aluminium, and 10.65 divided by 35.5. So the ratio here, or sorry, the moles there is obviously 0.1, and we have here 0.3. So 0.1 over 0.1 and 0.3 over 0.1 means we have a 1 to 3 whole number ratio, and we have a compound of aluminium chloride, AlCl3. If we take iron, we have, if you pause the video now, I will do it. We have Fe, and we have oxygen, so 1.68 over the 56, we have 0.48 divided by 16, which gives us 0.03, nice round-ish number, and 0.48 divided by our 16 gives us again 0.03. So if we divide both by 0.03, I shouldn't really need to do this for you guys, which gives us a ratio of 1 to 1. So we have indeed FeO. Right, let's have a look at this. 1.6 grams of sulfur, so we have sulfur was heated with oxygen and the mass increased to 4, so we've got a little bit more calculating to do. So we started off with 1.6, the mass increased to 4, so therefore 4 minus 1.6, or in other words, 2.4 grams of that must have been oxygen. So the RM of sulfur is indeed 32. So if we do 1.6 divided by 32 is 0.05, sorry. And if we do 2.4 divided by our 16 is 0.15. If we divide both of those by the smallest, we will get a ratio of 1 to 3, so that is indeed sulfur trioxide, or SO3. Okay, so we have lead chloride this time was found to contain 82.8 of our lead and 28.4 of our chlorine. Again, pause the video and have a go at these, please. So our lead chloride therefore works out to have an empirical formula of PbCl2. I didn't do the working out there because I'm hoping that by now you've kind of got the gist of this. Okay, right, this one's a little bit more complicated, so I want you to have a good hard look at it, okay, and a good think about it. Alright, so name the compound used. Well, the compound used is magnesium oxide. Calculate the mass of oxygen that has been added. Well, we started off with magnesium 0.48. We ended up with the mass of the new compound being 0.8, so you must have added this quantity of oxygen, which should work out at 0.32. The RFM of magnesium is 24, so 0.48 divided by 24 gives us a 0.02, and our 0.32 divided by our 16, okay, gives us our 0.02 as well. So it's a 1-to-1 ratio. You can see that quite clearly, I would like to think. Okay, and therefore you get MgO. Okay, we'll take now one that is, again, I suppose a little bit more difficult in that we now have 3 elements to deal with in the first one. Okay, but really the process by which you do the calculation is exactly the same. So number 7, which is the first one here, we have 1.48 of a calcium compound, contains calcium at 0.8 grams, it contains oxygen at 0.64 grams, and it contains hydrogen, sorry, at 0.04 grams. So if we do that over 40, do that over 16, do that over 1, we should end up with a ratio of CaO2H2. And for those of you who are on the ball, you might recognize that as calcium hydroxide. Okay, so I'll do question 8, and now if you want to pause the annotation or the video, and we'll have a look at point 8. So this time we go back to our old friend water of crystallization. So this time we're dealing with a compound, but it's exactly the same, except instead of trying to find out the molar ratio of elements to each other, we're trying to find the molar ratio of copper sulfate to water. So we've got to work out the moles of the copper sulfate first, and then we work out the moles of the water. Okay, so 49.9 of a sample of copper sulfate was found to have 18 grams of the water. So it's not a fantastically worded question to begin with, but so we'd 49.9, so we need to work out the molar mass of the copper sulfate here, which is 64 plus 32 plus 16 times 4, which is again 64. So we've 64 plus 32 plus 64 gives us an RFM of 160, and our water on its own has an RFM of 18. So if we have a look at the information that we are presented with, so we need to work out the moles of the moles of the copper sulfate. So let's just do that. 49.9 minus 18. So equals. Okay, so we had 49.9 grams of a sample, and 18 grams of the water was lost, which means we have therefore got 31.9 grams of the copper sulfate in that sample, and if we divide that by that, we get a value of, so it lost 18 grams of water, so the mass of water lost was 18. Okay, the moles of water must be 18 over 18, which is 1. So the ratio of water to copper sulfate is 0.2 to 1. That to the nearest whole number then is 1 to 5. So therefore X, or indeed the water of crystallization, must be 5. So our answer for the examiner is simply 5, because all we had to do was calculate X. But the formula, if they asked you for the formula, would be like so. Okay, this one here is an examination question. Okay, so it asks us to first of all calculate the number of moles of carbon atoms present. So again, you can pause this and come back and I will do the question. So if you pause now, I will work through it, and when you hit play again, the answer should unveil. So we have 1.44 grams of carbon, so it asks us for moles of carbon atoms. So it's 1.44 divided by 12, which is 0.12. We then have to calculate the number of moles of hydrogen atoms. We've 0.36 hydrogen atoms, note, which is a very simple 0.36 divided by 1 is 0.36. So we had to use our answer then to work out the empirical formula. So we simply take the smallest one and we divide it into both. So in other words, 0.36 over 0.12, which is 3, and 0.12 over 0.12, which is 1. So our answer to that is 1 carbon to 3 hydrogens. Now that is the empirical formula. Now the molecular formula then is the actual number of moles of carbon and hydrogen in a compound. Remember, empirical formula is the simplest number of moles. So given the formula mass of the hydrocarbon is 30, work out the molecular formula. Well, if our simplest whole number ratio is 1 to 3, and carbon is 12 and hydrogen is 1, so in other words that is 15, but the mass of 1 mole of this thing is 30, well that only adds up to half, so 30 over 15 obviously is 2, so the molecular formula must be the empirical formula times 2. So therefore the empirical formula is converted to molecular formula by multiplying everything by 2. Remember, the ratio must be maintained at 1 to 3 carbon to hydrogen ratio. Name the hydrocarbon. Well, it's ethane, and the homologous series that it comes from, hopefully you all are aware that that is indeed an alkane. Okay, this is another one about working out water of crystallization. So again, if you pause the video, okay, I will do it and you can come back and check it. You look at the data very, very carefully on this video before you attempt it. Okay, right, I will do it now. You pause please and go and have a go at it. Okay, so we have taken a solid here basically and we have put it into a little basin. We have heated it very, very intensely and we have driven the water off. So the mass of the original evaporating basin, which is the little basin that we're heating it in, is that. The mass of the evaporating basin plus the hydrated salt is 61.63. So the mass of the actual salt that you must have used at the start must have been 7.5. So in other words, the hydrated salt had a mass of 7.5. So the aluminium nitrate, the whole sample that you put in at the start, was 7.5 grams. Now, the mass of the evaporating basin contents after heating, well, that must have meant that after heating you removed the water. So the mass went down from 61.63 to 58.39. That meant that you removed 3.24 grams of water. So the water here is 3.24 grams and the actual anhydrous salt must have been, so without the water in other words, was 7.5 minus 3.24 is 4.26. So we can now start working out moles of each of those substances, and when we get moles we can then work out the formulae. Right, so aluminium nitrate, okay, so if we work down here, has a formula like so. So we have 27 plus 14 times 3 plus 16 times 9, that is 213, and we had 4.26 grams of it. So 4.26 over 213 is a nice round number, so I'm confident that I'm going along the right route. And we had water, which was 3.24 divided by the RFM of the water, which is 18, gives me 0.18. So if I divide both of these by this value, I get X, I think it's actually N up there, is 9 in this instance. So hopefully you got that right. Let's have a look at the second question, similar question. So we had 2.65 grams of a sample of crystals were heated to a constant mass. So again, we heated these hydrated crystals and we were left with 1.35. So why was it heated to a constant mass? Removed all the water. Calculate the moles of the anhydrous sodium carbonate. Well, sodium carbonate being Na2CO3. Okay, so we have 23 plus 23 plus 12 plus 48. So we have an RFM 106, sorry. So 1.325 over 106 gives me that number of moles of the anhydrous calcium carbonate. Calculate the mass of water lost. Well, the mass of water lost is very simply 2.675 minus 1.325. So 2.675 minus 1.325 gives me 1.35 grams of water that have been lost. Okay, so if we turn over so we've got to use those answers to calculate our value of X. So our moles of water is 1.35 over 18 is 0.075. Sorry, that's moles of water. And if we go back to the sodium, carbonate, we've 0.0125. So sodium carbonate 0.0125. So if we take the smallest number, which is hopefully you all recognize as being that, and divide it into the biggest number, we get a nice round number, where in this instance x is 6. Okay guys, hopefully by the end of that you're able to work out empirical formula. Those of you who are doing triple O, you'll be able to work out molecular formula and do those last couple of past paper questions that I put on the end there. And that is us done for video 3 in the moles calculations. When I've got some time, I'll make a video on moles calculations involving balanced equations.